Okay, I think it's time. Thank you everybody for joining us today. And today is again our CHASSPARK and OTF-SIG online seminar series. And today we are very glad to have Professor Melda Uxu for the topic on FTN MIMO signaling from capacity analysis to practical constraints. I personally really like this topic because FTN is known for high spectral efficiency, and the MIMO is, of course, what we are using currently. So the combining of them two will be very great. I'll give a quick introduction to Professor Melda. Professor Melda is an associate professor in the Department of Electronical and Electronics Engineering at Middle East Technical University, Turkey. She received her PhD in electronical engineering from the Polytechnic Institute of New York University in 2007. Her research focuses on wireless communication theory, and information theory, with recent work on advanced MIMO systems and faster-than-Nyquist signaling. She is currently a TPC co-chair of IEEE Globecom Conference 2026 and serves on the editorial board of IEEE Transactions on Communications. Okay, without further ado, please join me to welcome Professor Melda for today's talk. Thank you.
Thank you very much, Xuangyang. Now I will be sharing my slides. Oops. What happened?
No worries.
After that much rehearsal. Okay, so do you see my slides?
Yes, perfectly.
Okay, and it moves, right?
Yes.
Okay. So hi everyone. Today I will be talking about what I have learned in the last 5 to 6 years about faster-than-Nyquist signaling. This subject has drawn my attention really a lot because it helped me question whatever I learned about communication theory from scratch. Can I really do the power calculations? Can I really do capacity calculations for band-limited systems? Everything I learned about signals and systems and communication theory, I had to go over all those topics once again. So in this talk, I will be mentioning the following subjects. So first, I will be talking about the capacity of multiple antenna faster-than-Nyquist systems. As a practical issue, I will go through the instantaneous-to-average power ratio analysis of FTN. These two items will be on Gaussian signaling, although I will be talking about QPSK in this third item as well. Then we will be talking about what the capacity can be for finite alphabet transmission with FTN. I will also talk about briefly about other application areas. What happens if you utilize faster-than-Nyquist transmission in multiple access channels? What if there are multiple users? Or is it really useful in finite block length transmission? And I will conclude my talk with the future of FTN systems, what I think about its future. So first, let's have a very simple introduction to faster-than-Nyquist transmission. So how do we transmit symbols? Right now, we use Nyquist transmission as I show here on the left. So, and these are for root-raised cosine pulses or sinc pulses. Your favorite pulse shape can be assumed. And we are basically transmitting them in such a way that there is no intersymbol interference imposed. So here, if I would like to sample the blue, if I like to receive the blue symbol, then at that sampling time instant, there is no intersymbol interference due to the pink, red, green, or cyan symbols. So all the other contributions are equal to 0. But if I transmit in a faster-than-Nyquist fashion, now the intersymbol intervals are shorter. That's why when I sample at the receiver side for the blue symbol, then the intersymbol interference due to the red, pink, green, and cyan curves are not zero. See, these are the intersymbol interference terms contributed due to the other signals nearby. So this is different than any intersymbol interference due to channel, because this is deliberate. We have introduced this intersymbol interference on purpose. So here on the left side in the Nyquist transmission, signaling time interval is T, Nyquist symbol period. Now we use an accelerated version, which is delta T, and delta is a constant in between 0 and 1. And this is specifically introduced by the transmitter itself, and we know the structure of the intersymbol interference. So having said this, let's go through the FDN literature. So first of all, this is another reason why faster-than-Nyquist transmission is interesting, is because it was first introduced in 1975 by Mozo, and he showed that if you are not willing to do symbol-by-symbol detection, if you allow yourself to do sequence detection, then you can actually have the same inter-sequence distance for delta equals 0.8 when you are using sync pulses with BPSK. So when I learned this result, I was really surprised. I thought, I have given these lectures on signals and systems so many times, this Nyquist sampling criterion. I never thought about the assumption, the inherent assumption of symbol-by-symbol detection or symbol-by-symbol reconstruction. So if you allow for sequence detection, then you can actually send your signals accelerated. You can allow for some level of aliasing in your signals, and that's completely okay. You can recover your original message. And from 1975 to 2002, there hasn't been much work. See, these are the list of number of conference and journal papers in all the years from 1975 to current date 2026. So up until 2002, we don't have many papers. But since then, the subject starts picking up, but rather slowly. So in 2003, there is a paper by Liveris and Georgiades. They basically extend the work in Mazo's paper to root-raised cosine pulses. So the first paper is, it has the assumption of sync pulses. Now the next coming paper, it talks about root-raised cosine pulses, and it also introduces the concept of coded FTN. So if you are deliberately causing some intersymbol interference, you can also introduce some channel coding into your system as well to get rid of the undesired effects of intersymbol interference. Then in 2005, there comes the paper by Rusek and Anderson, and they talk about the constrained capacity of faster-than-Nyquist transmission. And basically, Rusek has a very comprehensive work on faster-than-Nyquist transmission. It's very impressive. It starts from capacity expressions, and it also includes FPGA implementation aspects. So that is very comprehensive. In 2006, Ferreira and Kempf, they have a transactions on signal processing paper where they investigate the synergy between faster-than-Nyquist transmission and super oscillation. So this becomes very important, especially in optical communications. In 2015, there is this paper by Juhas, Feng, and Bashsi in Globecom, and they look into the capacity of MIMO FTN, but they only assume receiver side channel state information, and they look into the MIMO FTN capacity results. There is another comprehensive work on FTN by Daniel Kim, Especially, he has a very comprehensive PhD thesis on the subject as well. But this paper published in WCNC was very important. It has a comprehensive list of properties regarding the channel matrix of intersymbol interference introduced by FDN and the folded spectrum. The mathematical properties are established here. And in 2017, this paper by Bedir Ahmed and Yannick Ömeroğlu, published in Access, talks about low complexity receivers. So you introduce intersymbol interference at the transmitter, and you'd like to undo the effects at the receiver side. Of course, this requires, in theory, very complicated receivers, but they show that low complexity receivers are very well performing as well. So this is in 2018. There is a very interesting paper by, it's not paper, I'm sorry, at the Shannon lecture at ISIT, Ungerberg himself talks about faster-than-Nyquist signaling as a very promising subject. This is also briefly, the script of the talk is also published in Information Theory Society newsletter too. So if you're interested, you can go and check that reference as well. In 2020, Ganji Zhu and Jafar Khani, they have a communications letter paper. They talk about the capacity of single input, single output FTN systems. What is interesting here is that they cover for all acceleration factors, even if acceleration factor values are small, and we will understand in 10-15 minutes why small acceleration factors are hard to understand. And there is this paper in 2021 by Ishihara and Sugiura, published in Transactions on Wireless Communications. They talk about eigenvalue pre-coded FTN schemes. Pre-coding is also an important aspect of faster-than-Nyquist transmissions. So everyone whose name I haven't been able to mention here, please forgive me, because see, in the last 10 years, there has been a very significant increase in journal and conference paper publications. And I think this is different than other topics like integrated sensing or communications or intelligent reflecting surfaces. This is a subject which gains traction rather slowly. But I think once people understand the importance of the subject, this acceleration will be continuous. So here it's 18 plus 5 because 5 is early access papers at the moment. Okay, so now let's see the system model for faster-than-Nyquist transmission with multiple antennas. So here the figure is for a 2x2 system. Here the pulse shaping used at the transmitter side is P of t. The matched filters used at the receiver side is P conjugate of minus t. The channel gains are denoted with HIJs, and there is additive white Gaussian noise in the channel. And because we accelerate with a symbol period delta t, we will be sampling at this symbol period as well. So we assume there are L transmit antennas and K receive antennas. And just to understand the theoretical foundations, we assume a quasi-static frequency flat fading. So for a particular transmission, the channel gain matrix remains to be the same. And we will be transmitting n symbols for information theoretical results. We will be sending n to infinity. Then the transmit signal takes this form. So from the Lth antenna, I will be sending n symbols consecutively. So here are the data symbols. I put them on the pulse shape itself, and I will be sending a sum of all these symbols from one of the transmit antennas, the Lth antenna, and the output at the matched filter of the kth receive antenna then will be expressed as in this form. Here, the function g is the convolution of P and its matched filter. So this G of T is the equivalent pulse shape you have at the output of the matched filter here. So there is something interesting we need to pay attention to. Here, the additive white Gaussian noise is filtered and then it is sampled. Since this delta is not equal to 1, the noise samples at this point are correlated, they form a correlated Gaussian process. It's not a white process anymore. So after the sampling operation, the input-output relationship can be written in matrix form. So here, Y1 indicates all the symbols we receive, all the n symbols we receive from the first antenna. Here, the last item is all the symbols we receive from the kth antenna, and everything in between is written in this column vector. So here, all symbols, so here, in this input-output relationship, A's are the transmitted signals, and it will be multiplied with this large matrix expressed here. So actually, it will be the Kronecker product of the channel matrix H and the intersymbol interference matrix G. Why do we have the intersymbol interference matrix G here? Because when so maybe going back to this will be useful here. When I'm sampling for the blue signal, so the desired signal is the desired symbol is multiplied by G0, but then there will be contributions from G delta T, so the function sampled at delta T, the function sampled at minus delta T, the function sampled at minus 2 delta T. All these terms will have contributions as intersymbol interference. So when I transmit n symbols, the intersymbol interference will be expressed as this matrix G. So overall, this H tilde is the channel matrix from the transmitter to the receiver. So it is just composed of the channel gains here. So eventually, the output is expressed as the Kronecker product of the MIMO channel and the intersymbol interference channel. So it's as if right now we have a virtual big MIMO system. So how many transmit antennas we have? L transmit antennas, K receive antennas. So normally it would be a K times L system. But in this version, we have a big matrix H, and it is as if Kn times Ln big MIMO channel is formed. So we have too many input symbols, too many output observed symbols, and H models the dependency of the input and the output, and this capital sigma denotes the colored noise. And we'd like to calculate the capacity here. So that's why we need to calculate the mutual information and the input distribution that maximizes this mutual information. That's why we need to calculate the differential entropy for Y and differential entropy for noise. We need to take the difference. So after you do the calculations, the capacity expression can be written as usual in logarithm and determinant form. So this will be the whole expression. So a closer look to this, a closer look at this expression will be very helpful, and we'll see that, this is what we input into the system, because the transmit power constraint is also on that quantity. Okay, so this is the covariance matrix you choose for your input. And that is also present in the capacity expression. And this is the overall, it's as if this is the overall channel you observe. If you compare these two equations, now this is the capacity expression of a generic MIMO system, okay? So here is the input covariance matrix K, and here is the channel matrix times its conjugate, times its Hermitian. So if you have this kind of an expression, okay, we know how to calculate the optimal input covariance matrix. So in this case, the optimal input covariance matrix turns out to be this expression. So what does this mean? This means that we need to do, basically the first parentheses is the eigenvalue decomposition for the channel matrix H tilde, and the other one is basically having an inversion for the ISI matrix G. So if we are causing deliberate intersymbol interference as G, before transmitting the symbols, I need to process them with G inverse. And then, since I have multiple antennas, the amount of power I allocate to each one of my eigenchannels should be found using the classical water filling solution. This is how we need to find the solution. But here, I'd like to draw your attention to something, and that is, for this derivation, the acceleration factor should be large enough. Assuming that you are using root raised cosine pulses with roll-off factors beta, then your delta should be larger than a certain quantity. Otherwise, it turns out that this G matrix is not invertible. You can, for delta larger than this particular threshold value, you can express the capacity, information theoretical capacity expression. But here we can understand why the G matrix is invertible when delta is larger than a certain threshold. See, the eigenvalues are actually, they turn out to be the samples of the folded spectrum. If delta is larger than a certain threshold, then the folded spectrum, there is aliasing on the folded spectrum. There are no zero parts on the domain, and all the eigenvalues will be larger than zero, and this G matrix will be invertible. But if the delta is less than the threshold value, 1/1 plus beta, then some parts in the folded spectrum, in one period of the folded spectrum, some sections will be zero. That's why some eigenvalues, when n goes to infinity for infinite block lengths, some eigenvalues will be zero, and the G matrix will not be invertible. In that case, in order to find the capacity, you need to do the capacity calculation not in time domain. We need to do that calculation in the frequency domain using the folded spectrum approach. So we need to use this folded spectrum as our tool to calculate the capacity. And using Szygło's theorem, we can actually express the capacity expression. See, this capacity expression, this problem is valid. I'm sorry, not that one. This problem is valid whether G is invertible or not. But finding the solution when G is not invertible is not easy. So using Szygło's theorem, which ties the eigenvalues of these matrices with the folded spectrum, we are able to write the same capacity calculation problem in frequency domain. And this way, we find the optimal power, input power spectral density to be equal to this form. So if your folded spectrum is like this, over the support, over the region where the folded spectrum is non-zero, you need to you need to invert the channel so that your system is capacity achieving. So when you combine the result for delta larger than 1 over 1 plus beta and delta smaller than this threshold value, you obtain the capacity expression. So when you have a transmit power constraint, your capacity expression looks like this. So delta equals 1 corresponds to the Nyquist case. If you keep decreasing delta, okay, so this corner point here is equal to 1 over 1 plus beta. So basically, this is related with the bandwidth of your system, okay? So depending on your bandwidth, there is a threshold value, and up until that threshold value, your capacity keeps increasing, okay? But from this point on, if you keep decreasing delta, then there is no increase in capacity at all. This is because beyond this corner point, I'm saying corner point, but I don't mean anything about differentiability at that point. So it's the threshold value. Beyond this threshold value, basically, the amount of acceleration, which increases spectral efficiency, and the amount of intersymbol interference, which decreases spectral efficiency, basically cancel each other. So on one hand, you are sending symbols faster, but you are actually sending noisier symbols. That's why the overall effect cancels and the capacity does not increase at all. And in fact, this is the boundary, this flat value is exactly equal to the capacity that you can achieve in a band-limited system. So this is basically the best you can do, and FTN helps you achieve that best with accelerated transmission. So, but here I'd like to answer a question before, sorry, so let me first talk about the following. Yeah. So here, let's first focus on the black triangles and the red triangles. So I know some people think that if I invert the folded spectrum like this one, I end up having a rectangular, if the effective bandwidth I'm using is rectangular, and in time domain that corresponds to the sinc function, and that's why this is not that meaningful, and we shouldn't be basically doing optimal power allocation like this. So what if I do power, what if I use constant power over my spectrum? In that case, instead of black triangles, I obtain red triangles, but still with respect to the Nyquist transmission, a significant rate increase is achieved. So what is so what about these squares, black squares and red squares? So there's something very interesting about the SNR definitions in the literature on FTN. So some papers assume the transmit power. They assume that the transmit power at point A is fixed. So they say that they have power amplifier limitations. That's why this power cannot be larger than a certain quantity. We are transmit power limited. And sometimes some other papers assume that after the sampling operation at the receiver, energy per symbol is fixed at point B. These are two different assumptions, and they are meaningful in different settings. If you are operating at a high power regime where power amplifier limitations are significant, then obviously you have the first assumption and the triangular curves are important for you. But if you are more interested in energy efficiency, then the energy constraint at point B may be more important for your device. That's why what happens to the capacity expression if you have energy per symbol constraint at point B. So basically, if you have energy constraint at point B, this accounts for transmitting more power for smaller delta at point A. Okay, that's why if you keep decreasing delta beyond the threshold point, capacity keeps increasing. So if you use optimal power allocation, you have the black squares. If you use uniform power allocation, you have red squares. So the top two curves are for energy constraint at point B, and the bottom two curves are for power constraint at point A. So this actually seems very nice because yes, you are inputting more power into the channel, but you keep energy per symbol fixed at point B, and you are observing larger spectral efficiency at the receiver side. Okay, when I talked about the capacity expression, I said that what we need to do to achieve capacity needs to be optimal both in space. So whatever I do among my antennas has to be optimal, and also whatever I do to mitigate intersymbol interference. So you may call this to be pre-coding in time or optimal power allocation in frequency. So here S and F stand for space and frequency. So OS means that optimal power allocation in space. OF means that optimal power allocation in frequency. So here, the black curve is the best one. You do the best power allocation you can do. And this is the capacity achieving scheme. But if you don't want to do pre-coding for FTN, you want the intersymbol interference to remain present. You don't do any pre-coding, but you do optimal power allocation among your transmit antennas, then you get the red one. So once you switch to suboptimal power allocation in space, so you don't do water filling among your antennas, then you are down to these two bottom curves, and they don't differ much whether you do optimal power allocation in frequency or not, whether it is optimal or suboptimal here. So if you are not willing to increase your complexity due to FTN, you will still be able to reap the majority of the gains just by optimal power allocation in space, and that is what we usually do for MIMO communications anyway. So from green and blue curves to the red one, it's a significant gain already. So we don't have to do pre-coding for FTN on top of that. That's not that much necessary. So this is just a simple curve that shows that SISO curves are here, and by using multiple antennas, you can increase your spectral efficiency significantly. But here in this graph, what I'd like to emphasize is the following. So here, of course, if you can operate with sync pulses at Nyquist transmission, that is the red one for MIMO and red dashed one for SISO. So that is the best. With FTN, we are not claiming that you do something better than sync pulses with Nyquist transmission. We are saying that once you switch to root-raised cosine pulses, and that is what we use in practice, if you have to have a different pulse shape, then Nyquist transmission is quite inefficient. Then you are down to this black curve for MIMO here, SISO here, dashed one. In this case, if you resort to faster-than-Nyquist transmission, you can, by adjusting your acceleration value, you can make this black curve into pink, pink into blue. Okay, so here, this will be the blue one, is basically plotted for the threshold acceleration factor. So if you keep increasing your acceleration factor beyond the 0.67, if you keep it decreasing, the capacity in as spectral efficiency won't be increasing any more as long as you have transmit SNR constraints. Okay, so these results here, this slide, I'm not going to go into the details, but we have also extended these results to frequency selective channels as well. So basically, frequency selectivity is a form of intersymbol interference. FTN results in another form of intersymbol interference. So basically, you can deal with them together. That's and their joint design is nothing complicated. It's a very straightforward application. Okay, so given that we have this transmit and receive SNR constraints, we also need to talk about instantaneous to average power ratio. So this is especially important if you have the received SNR constraint at the output of the sampler at the receiver. So that's why we define the IAPR as the instantaneous energy level of the signal at the output of the ELF antenna divided by the average power of that particular antenna. So the IAPR, it's sufficient to calculate for each one of the antennas separately. Since this is instead of working with IAPR directly, we first look into the complementary cumulative distribution function. What is the probability that IAPR is greater than or equal to a certain threshold? Then we average this quantity over one period. So we are basically talking about the average CCDF, complementary cumulative distribution function. And basically for Gaussian and QPSK signals, this can be calculated. And found analytically. And here are the results. For Gaussian symbols, if you have a transmit SNR constraint, okay, basically your average CCDF does not change with delta. So basically you are immune to IAPR. It doesn't matter how accelerated you transmit, your average instantaneous to average power ratio CCDF will be the same. So let's see how this changes for QPSK constellations. So here, for QPSK, if you have transmit SNR fixed, okay, this will be, your system will be less affected from delta variations. See, the blue one is for 0.25 and the pink one is for 0.1. So accelerating the symbols more does not mean that your IAPR is significantly increased if you have transmit SNR fixed. But that's not the case if you have received SNR fixed. Remember, in order to keep the received SNR value fixed for a smaller delta value, actually we input a larger power value. So it's actually a very simple calculation. Power is equal to energy divided by time, right? So if you are, we can express this as energy equals P times the time interval. So if your delta value is smaller, your delta value is smaller. That's why you need to compensate for that difference. That's why if you have a received SNR constraint, in that case, a smaller delta value means that you need to have a larger average CCDF value. Okay, so you need to be careful. And if you are having a received SNR power constraint, power amplifier nonlinearities should be taken into account. So this is another result. And here, we try to look into the pulse shaping problem for faster-than-Nyquist signaling. So yes, we know that in practical systems, root-raised cosine pulses are commonly used, but that is for Nyquist transmission. If we knew that we would be using faster-than-Nyquist signaling, maybe there is a better pulse shape, and that is shown here in this figure. The horizontal axis is the bandwidth in which you contain 90% of the pulse energy. The vertical axis is the bit error rate, and the color coding is for the average instantaneous-to-average power ratio. So we basically want to be in the blue regions. And let's see where the RRC line is. So for different roll-off factors beta, you will be able to obtain this red dashed line here, okay? RRC pulse is here. If you do, for example, beta equals 0.7 is this diamond point here on the figure. If you do an optimization with genetic algorithms, you can operate on this orange triangular point. With particle swarm optimization, we've been able to get to this dark green point, and this light green point has been, we have achieved that point with a machine learning technique. We have optimized the pulse shape design using a machine learning technique, and we have been able to almost minimize the bandwidth with the smallest peak to average power ratio for a very small bit error rate value. So all these aspects has to be optimized simultaneously. So you can't just focus on bit error rate, you can't just focus on bandwidth or IAPR. They have an interplay in between each other. Okay, so let's say now I will talk about more practical aspects of faster-than-Nyquist transmission. What if we have a frequency selective channel? We have finite alphabet symbols. So Gaussian signaling is very nice. Yes, we learn about the information theoretical channel capacity. But as we all know, information theoretical capacity requires Gaussian symbols and infinitely long number of infinitely many symbols to be transmitted to be achieved. That's why we need to investigate the problem with finite alphabet symbols and what happens if we transmit only n symbols at a time. This is a very important practical constraint. So that's why we propose pre-coding at the transmitter side. So before pulse shaping and FTN modulation, we pre-code the input data S with this pre-coding matrix D, and we form the data A, as in this equation, and we do scaling to satisfy the symbol energy. And we transmit in FTN modulation. We accelerate the pulses and transmit them in a faster fashion. And at the output of the matched filter, we will receive all the n symbols. Of course, we will also be receiving symbols from all j taps here. And this will be the received signal, and still the g function is the output pulse shape at the output of the matched filter. So this whole thing can again be written in matrix form, and after including transmission of FTN symbols through a frequency selective channel with J taps, the input-output relationship is again written in matrix form, and here the overall channel matrix C turns out to be a banded Toeplitz matrix. So this turns out to be a very important property. It incorporates both the FTN-induced intersymbol interference and the multipath-induced intersymbol interference. So all the effects are represented by this channel matrix C. Okay, so interestingly, if you add cyclic prefix and cyclic suffix to this channel matrix C, basically you will convert it into an equivalent cyclic matrix. So for cyclic matrices, just like in OFDM, it is known that the DFT matrix diagonalize this cyclic matrix. So once you insert cyclic prefix and suffix, the DFT precoding and IDFT receiving, or vice versa, it turns out to be the eigenvalue decomposition for your channel, and you can parallelize everything. So your eigenvalues are eigenvalues due to your FTN transmission are lambda k, and hk are the coefficients you observe due to the frequency selective channel response. And in this case, depending on your delta value, if your delta value is smaller than your threshold, some eigenvalues will be approximately 0, and approximately this many eigenchannels will be active, and the remaining ones will not be active because the channel gains will be extremely small. Okay, so for this, we use the results by Ungerberg from 1982, and we calculate the constraint capacity with finite alphabet inputs. So the total rate, we write the constraint capacity, and we first average it over the active eigenchannels. And overall, the spectral efficiency in bits per second per hertz is equal to this quantity. So this is the channel capacity for each one of the eigenchannels. We sum them all together and divide by the number of parallel channels we have, which is n. And it turns out that it can be written, so nr of them are active. That's why this is the overall constraint capacity we have in bits per second per hertz. So let's look at how this constraint capacity calculation looks like under transmit SNR and received SNR constraints. So let's first look at received SNR case. Here, we have compared different modulation schemes under the same spectral efficiency. See, QPSK has delta value equal to 0.2, but 16 QAM has delta value equal to 0.4. So everything has spectral efficiency in logarithm 2. Size of the modulation scheme divided by delta in bits per second is fixed for all curves. But if you look at the spectral efficiency, then what you observe for QPSK and 16 QAM, for example, is like in this curve. So an accelerated with a higher acceleration, I mean smaller acceleration factor, we are sending faster and faster. This one is more efficient than a slower 16 QAM scheme. See, this pink region is larger than the red curve for some SNR values. When SNR Rx is small, you may resort to a smaller constellation with a smaller acceleration factor. So smaller constellations can be useful. This graph tells us this fact. And here on the right-hand side, we have a transmit SNR constraint. And with Nyquist transmission, with root raised cosine pulses, with adaptive bit loading, so we have created some parallel channels, right? So over those parallel channels, if you do adaptive bit loading, this is what you can achieve with Nyquist. But if you resort to FTN, faster-than-Nyquist transmission with adaptive bit loading, this upper curve will be what you achieve. So there is some spectral efficiency increase with FTN, even under the same fixed transmit SNR constraint. And finally, I'd like to mention the following. So yes, we have added some cyclic prefix and cyclic suffix so that the finite block DFT precoding is optimal, but obviously this results in some overhead losses. That's why we are also interested in the case of mismatched achievable information rate. So your matrix, that C matrix, which explains the intersymbol interference due to the channel and intersymbol interference due to FTN. If you leave it as it is, you don't add cyclic prefix or suffix to it, and you still do DFT precoding, okay? What is the achievable information rate? What is the practical achievable information rate for this case? So this is kind of an upper bound. This is what you achieve with sync pulses. This one is Nyquist transmission with root-raised cosine pulses. So if you have the matched case for delta equals 0.3 and delta equals 0.5, they have the same performance because we have SNR-TX transmit side SNR constraint. In that case, if it is the matched case, as I have just talked about with cyclic prefix and suffix perfectly matched case, then this is the capacity. And the achievable information rate for the mismatched case actually converges to the optimal value once the value of n increases, okay? And actually, you don't need very large n. Approximately 1,000 symbols is sufficient to achieve the optimal DFT precoded spectral efficiency performance. Okay, so I'm not going to go, due to time limitation, I'm not going to go into the details of asynchronous multiple access channels. This is another topic that I wanted to emphasize. But let me just say the following. Faster-than-Nyquist transmission is actually very useful in multi-user settings as well. So once you have this root-raised cosine pulse or any practical pulse shape assumption, anything other than sync pulses, then up until this point in the presentation, we have discussed that the single user transmission rates can be increased. Okay, instead of having this rate by Nyquist transmission, you can get to this rate, or with a smaller acceleration factor, you can get to this rate with FTN. So what is interesting in this curve is that FTN also increases the sum rate. So it's not just the individual rates that have increased, but it's also the sum rate that has increased with FTN. So thinking that we have numerous users in a practical commercial system, this sum rate increase is also quite beneficial, I think. The last topic that I'd like to mention is that faster-than-Nyquist transmission will be especially important in finite block length transmission where real-time operation is important. See this figure? So the top one is the Shannon capacity. You have, so this is the maximum channel coding rate in bits per second per hertz. And horizontal axis is different delta values. For this whole graph, bit error probability is assumed to be 10 to the power minus 6. The graph is for a 2x2 MIMO system, and transmit SNR is equal to 20 dB. So in this case, this is the Shannon capacity you have. So this is for 20 symbols, 200 symbols, 500 symbols, 1,000, 2,000, and so on. So after a certain point, increasing the value of n is bringing diminishing returns. And let's say we fix the maximum channel coding rate at 6 bits per second per hertz. Okay, let's fix this horizontal line. So for 1,000 symbols with Nyquist, 1,000 symbols, and with Nyquist transmission, whatever bits per second per hertz you achieve the same rate at 200 symbols with 0.87 acceleration factor with faster-than-Nyquist transmission. So this point and this point, although they have different number of symbols, they basically have the same maximum channel coding rate. So basically, the rate and the number of symbols they attain, they attain a certain bit error rate is different. So I believe that's why Faster-than-Nyquist will be very important in finite block length transmission. So now let's have as concluding remarks, let's talk about some application issues of Faster-than-Nyquist transmission. First of all, every one of us is interested in applying OFDM and FDN together. So for this, you basically can implement it in two ways. First, you can basically overlap the subcarriers on top of each other, just as in spectrally efficient frequency division multiplexing. Or you can send OFDM symbols faster in time domain. So we are still investigating which one turns out to be better, but obviously FTN and OFDM can be integrated together in an easy way. And there will be applications in hyper-reliable low latency communications, just as I have mentioned now. Finite block length and FTN have a very important synergy in between. So this should be explored in detail. And for integrated sensing and communications and for satellite communications, the advantages, PAPR properties, peak to average power ratio properties of FDN signaling, switching to smaller constellations with higher acceleration, but attaining better peak to average power ratio properties will be quite useful in both ISAC and satellite communications. And just like we can accelerate signals in time and frequency, we can talk about acceleration in the delayed Doppler domain. So that also seems to be a promising research direction. And maybe an interesting problem is to reduce any complexity or energy consumption increase due to FTN, and maybe for unresolved cases, artificial intelligence and machine learning can provide some interesting solutions. So let me conclude my talk. I have talked about the MIMO FTN channel capacity for all acceleration factors. And with this analysis, basically, we have learned that there is a significant difference between a transmit SNR constraint and a received SNR constraint. Are you keeping your output transmit power the same for all methods under comparison? Or are you keeping energy per symbol fixed at the output of your matched filter after sampling? Is that what you keep fixed? So we just need to clarify this point because it changes how we interpret any result we have in FTN. Again, due to this transmit or receive SNR difference, IAPR behavior for Gaussian signaling and for QPSK signaling or any finite modulation can be quite different than each other. And we need to be very careful about the backoff values when nonlinear amplifiers are used. Pulse shaping optimization for FDN transmission is also a promising direction. So FDN seems to require its own optimal pulse shape to be found, to be standardized. And once you complete the theoretical analysis, then the question turns into, the focus turns on to practical applications. So if you have finite alphabets, what is the constraint capacity? Is FTN still useful? Can we do pre-coding? What kind of an equalizer should we use? Should we do both pre-coding and equalization at the same time? Or depending on your application, in satellite communications, maybe the receiver is it doesn't have any computational burden. So in an IoT communication system, for example, you can send everything with FTN in a short time, and the receiver can do everything together. So all the practical issues become important. What is the constraint capacity for different equalization techniques, different pre-coding techniques? Also, can we really make use of FTN in asynchronous multiple access channels, or can we make use of FTN in broadcasting, for example, in a downlink communication scenario? There is also a synergy between FTN and finite block length transmission, and there are so many application areas of FTN. So we have briefly gone through all these areas one by one. Hopefully, I have been able to convey some of those messages to you. And finally, I'd like to thank my collaborators, Zichao Zhang and Professor Halim Yanıkomeroğlu from Carleton University, Gökhan Güvensen from my own university, Middle East Technical University, Xuan Yangli from Technical University of Berlin, and Oğuz Kışlal from TÜBİTAK, Turkey. So thank you very much for listening to me, and I'll be happy to answer any one of your questions.
Thank you, Melda, for the great talk. It's very informative, and I really like your ideas of FTN signaling, and especially on its combinations with other technologies. We have received several questions, which I found very interesting, and I hope you have the time to answer it.
Sure.
The first one is about the MIMO FTN. When you are presenting your work, especially saying that when combining MIMO with FTN, you are able to get a higher spectral efficiency. However, especially, for example, when you are in the presence of a high channel mobility, and in this case, does that require that for MIMO FTN to perform well, you need a much better channel state information?
Yes, of course, that's under mobility, that's important. So yes, this is a very nice practical question. In Nyquist, how is Nyquist, the channel state error, does it affect Nyquist transmission and FTN by the same amount? Maybe FTN loses more. That's valid. We are looking into channel estimation with FTN. Yeah, we need to do some research on that. But if you have sufficient diversity levels, FTN turns out to be a good candidate for channel estimation as well. It has the potential to decrease your pilot length, for example.
Right. Yeah, I have also a follow-up question on that. So when you are targeting, for example, for fixed spectral efficiency, do you prefer to add more antennas given the power budget, or you prefer to accelerate your simple transmission faster?
I guess it all depends on where we are on this curve, right? Here, for example. Yeah, and also the slopes keep changing a little bit. That's why it also depends on the SNR constraint. So maybe if I have high SNR, right, I'd rather use more antennas. But yeah, I can't say for sure because for SISO slopes, they are all, I guess first you need to have MIMO. And if you have to choose between the two, MIMO brings in more gains. But once you have MIMO, please have FTN as well.
Yes, I agree with.
I think this also it is also consistent with this figure. So C power optimization in space over your antennas is more significant than having optimal power allocation in FTN. So that multiple antenna thing brings a uncomparable spectral efficiency gain, no matter what. It's a multiplicative factor in front of your capacity expression at all times. But with FTN, you can manipulate that logarithm. For each multiplexing gain, you can actually increase your rate.
Yes, I agree with what you mentioned. And in my opinion, also the channel state information, no, sorry, the channel condition is also important. For example, if in the channel there's not so much degree of freedom, adding more antennas does not help you a lot. Instead, you need to better exploit the degree of freedom you have in the channel. Yeah. Also, in addition to what you had mentioned, especially in the presence of this figure, I have another question. Recently, there are quite a lot of discussion on the so-called continuous aperture MIMO, which means that they give up on the antenna spacing in the spatial domain. I wonder, do you consider to apply the idea of FTN in the spatial domain directly by somehow transmitting more symbols within the same aperture size?
Wow, that's a very good question. I have never thought about it. Okay.
No worries.
Yeah, that's very good. I don't know.
Okay, thank you. There are other questions. What do you think is the biggest obstacle for FTN to be adopted in 6G and beyond? Is it because of the requirements on the channel state information or the non-linearity of the high power amplifier? Or it's just that people in industry are just reluctant to try something new?
I think this last one, because remember, so I'll go back to this slide now. So FTN has been here for a while, and until now it hasn't been applied. And I think first it was considered in Bell Labs, and they didn't think that it's a very promising method, maybe because of the available receivers at that time. So maybe increasing complexity at the receiver side, or having more capable transmitters capable of doing pre-coding was not present. So they didn't think that this transmission scheme is very promising. So this somehow had a place in the community. So whenever I find something nice about FTN, I always ask myself this question: this is something so nice. Why have not someone else found that result before me? Why did they not consider this? I think it's because of this distance they have between FTN and our thoughts. So I don't think that complexity is a very big issue, because I mean, and power backoff is definitely not an issue, because the reason is the first thing I expect when FTN is incorporated in the standard, instead of operating at this point, we will be operating at this point. And this one is for fixed transmit SNR case, and even for QPSK, this change does not have a significant effect on peak to average power ratio. So even if we move from delta equals 1 to delta equals 0.67 with QPSK transmission, the instantaneous to average power ratio will not be increased a lot. And if sampling, okay, at this point requires sampling a little bit faster, but our systems are capable of operating at different bandwidths. So, so if the system is already capable of transmission and reception at bandwidth 1 over delta t, then it means that the equipment, the hardware, is already capable of sampling at that value. So I don't think that sampling at the receiver side is going to add a lot to the complexity issue either. So just to go from here to here, I don't see any issue. And if we are talking about operating somewhere here, then there will be some very nice trade-offs. So maybe there will be sweet spots on the IAPR curves that, yes, you slightly increase your IAPR, but significantly increase your spectral efficiency. So the trade-off will be very nice. So even in fixed receive SNR case, I think that FTN does not have a very significant issue. It should be, as a theoretician, I can easily say this, right? It should be practically implemented with no problems.
Right. Okay. Another question is related to the combination of FTN with OFDM. We are mentioning that there are several ways to combine FTN and OFDM. Do you suggest that we need to abandon the existing low complexity equalizers for OFDM because FTN always gives some non-orthogonality there? So does it demand we have to use some high complexity equalizers?
In the literature, there are also low complexity equalizers for FTN as well. So I have not studied composite receivers for OFDM and FTN together. So I can't say for sure how much complexity increase that will incur, but we should do the research and see. Yeah, there are some extremely low complexity receivers out there for FTN.
Right. Okay. I think we have two more questions. Another one is about the combination of FTN with delayed Doppler domain signaling. So basically, when we're talking about the combination of them, do you suggest that we need to do a two-dimensional compression in both delay or Doppler, or we can just do a one-dimensional compression in either time or frequency?
Theoretically, both should be explored, just like we explore time and frequency together in FTN. So right now, my research is mainly focused on time domain compression, and recently I have started looking into joint compression, both in frequency and time. Yeah, theoretically, we should search for that together.
Right. Okay, so the last question, I think this is from a very interested reader who is interested to know more about FTN. So this person is asking about what is the typical selection on the acceleration factors? What are the typical values that we should be interested in?
If it is the transmit SNR constraint, there is no point in accelerating beyond the threshold value, and you can accelerate up until the threshold. So why stop here at 0.8, for example, while you can achieve something larger? So go to the threshold, and that should be a very good value to operate. Of course, when you have practical constellations, when you have receive SNR constraints, that optimal delta value may change. So actually, finding the optimal modulation size and the acceleration factor pair is a very interesting research direction.
Right.
But for finite, transmit SNR fixed cases, basically just use delta at the threshold value, and that should be a good selection.
Yes, I agree with you. Thank you, Melda, for today's talk and also your kind answers to all the questions. I think given the time that we should probably go to the end of this presentation. And thank you again for this great work.
Thank you very much for inviting me.
It's always a pleasure. Okay, see you guys. Bye-bye.
Goodbye.
Bye-bye.